Hello everyone, my name is Debarnav Mitra and I am a PhD student in the ECE department at UCLA, and today I'll be talking about my research on concentrated stopping set design for coded Merkle tree, improving security against data availability attacks in blockchain systems. This work was done with my lab mate Lev Taus and my advisor Professor Lara Dolache. Blockchains are distributed ledgers of system transactions that by design are tamper-proof, and they are used to create what is called the decentralized trust platforms. And initially, they were proposed for applications in the field of finance and currency. But due to their decentralized nature, blockchain systems find applications in diverse fields like healthcare services, industrial IoT, supply chain management, and many more. One of the central problems in blockchain systems is that of prohibitive storage overhead. So because the blockchain systems are decentralized, there is no central entity who is maintaining the blockchain ledger, but this ledger is maintained by a network of nodes, and each node maintains a local copy of the ledger. And this causes significant storage overhead. For example, the Bitcoin ledger is currently around 350 GBs, and the Ethereum ledger is of the size of around 800 gigabits. And this amount of storage is prohibitive for resource limited nodes. And the solution for this is to introduce light nodes. So subtle blockchain systems run light nodes, where these nodes do not store the entire block of the ledger, but only store the headers corresponding to each block. So for Ethereum, this would amount for a storage space of around 1 gigabyte. Now, by using the header that is stored in the blocks, these light nodes can verify the inclusion of a transaction in a block. But because they are not storing all the transactions, that is, they are not storing the entire block, they cannot verify the correctness of a transaction, and they rely on honest full nodes for fraud notification of any incorrect transaction that might be present in the block. And it is known that systems that have light nodes and have a dishonest majority of full nodes are vulnerable to data availability attacks. And in this attack, what the adversary does is it creates an invalid block. That is, it creates a block that has some invalid transactions, and it sends this invalid block to the full nodes, honest full nodes, but it hides the invalid portion, and it sends this header to the light nodes. Now, honest full nodes cannot verify what is missing. They do not have access to these missing transactions, hence they cannot verify them and cannot create fraud proofs. And in return, light nodes receive no fraud proofs from the honest full nodes, and hence they are forced to accept a header of an invalid block, which is a problem. Hence, light nodes must ensure data availability, and they do so by randomly sampling chunks of the block. So whenever they receive a header from a block, they ask the question, is the block available? And they do so by randomly sampling few chunks of the block. And to improve the efficiency of sampling, or to improve the efficiency of the number of samples required to achieve a certain probability of detection, erasure coding is used. And it has been shown that LDPC codes are suitable for this application because of the high storage efficiency. However, LDPC codes have problems, and the problem is the existence of certain structures in the tenor graph of the LDPC code, which are called stopping sets. And let me explain what the operational meaning of these stopping sets are. So if the variable nodes that are corresponding to this corresponding to the stopping sets of this LDPC code are hidden, that would prevent a full node that uses a peeling decoder from decoding the original block. So say we have this original block which is coded using an LDPC code to generate a coded block, and the adversary hides variable nodes corresponding to a small stopping set. In that case, the peeling decoder will not be able to recover back the original block, and hence a fraud proof will not be created by the full nodes, and hence a successful data availability attack will occur. And because now the adversary is hiding such a small fraction of all the coded chunks, if we calculate the probability of failure, that is the probability that the adversary does not request for these coded, does not request for the portion that is hidden, in that case, the probability of failure here comes out to be pretty large. And in this work, what we do is we design specialized LDPC codes and provide a coupled sampling strategy to significantly lower the probability of failure. And our design idea is what we call the concentrated stopping set design. So in this work, what we do is we consider an adversary which randomly hides a stopping set of a particular size. And for such an adversary, what we would like to do is to concentrate these stopping sets to a small section of variable nodes. That is, make all these stopping sets, make a small section of variable nodes be part of a large fraction of stopping sets, and then greedily sample those variable nodes to get a low probability of failure. Therefore, our coding problem becomes that of concentrating stopping sets. So the question is, how do we concentrate stopping sets in an LDPC code? We know that stopping sets are interconnection of cycles. Hence, we concentrate cycles to concentrate stopping sets. And we concentrate cycles by modifying the well-known progressive edge growth algorithm, which is a known algorithm in coding theory literature to design LDPC codes. And we call our algorithm the ECPG, or the entropy constraint progressive edge growth algorithm, and we use entropy as a measure to concentrate cycles. So the progressive edge growth algorithm can be seen as an iterative algorithm where for every variable node, it decides which check nodes to connect to. So it is basically a check node selection criteria. The algorithm depends on what criteria you use to connect check nodes to the variable nodes. And in this algorithm, whenever new cycles are created, what we do is we find check nodes which are most distant to the current variable node, so that the cycles formed are of the largest size. That will result in the stopping sets being formed to be of the largest size. And then what we do is we want to select check nodes that concentrate the cycle distribution, and we use entropy. The question is, how do we select a check node that concentrates cycle distribution? And we use entropy as a measure. We know that uniform distributions have high entropy and distributions that are concentrated have low entropy. And because we want the cycle distributions to be concentrated, we select check nodes such that the entropy of the cycle distribution is minimized. So we select such a check node that results in the minimum entropy of the cycle distribution, and then we update the cycle distribution to be used in the next iteration of the PEG algorithm. And our sampling strategy after we have concentrated cycles is to greedily sample variable nodes that are part of large number of cycles. And we would like to compare it with random sampling, which was used earlier in literature, where every variable node is sampled with equal probability. So now let's look at the simulation results for our coding construction. So we plot the probability of failure for a stopping set of size mu. As a reference, we plot this black curve, which is when we use random sampling on a randomly constructed LDPC code, which was used earlier in literature, that resulted in a stopping set of size 6. Now, if we use the ECPG algorithm, but still use random sampling, because larger stopping sets are formed, that is of size 10, 11, 12, we get a reduction in the probability of failure. Now, instead of using random sampling, let's move to greedy sampling, but keep using the original PEG algorithm, because now we use greedy sampling. That is, we sampled the variable nodes based on the cycle distribution. We get a further reduction in probability of failure. And then finally, when we use the entropy constraint progressive edge growth algorithm, where we have concentrated the stopping sets and then use greedy sampling strategy on this code, we get the further reduction in probability of failure. Hence, we conclude that concentrated LDPC codes coupled with a greedy sampling strategy improve the probability of failure of right node detection of data availability attacks. So the results shown in this presentation were published at the information theory workshop, which was held recently. And it can also be available, it can also be accessed at the archive link shown over here. And recently, this work received the Best Poster Award at the IEEE North American School of Information Theory. And these are some of the other references used in these slides. And I thank you all for your attention. And I hope you enjoy the rest of the presentations at this venue.